Welcome back. This week we're going to talk about Chapter 12, Discriminant Analysis. This is a method for classification, and it's been around for a long time, has a very good track record, and in certain circumstances it can be even better than logistic regression in terms of efficiency. This type of analysis has been around for a long time. Much before data mining, it was used to classify organisms, identify species by their skull, and also to look at differences in fingerprints. In business, it's used to do any sort of classification like we've talked about previously, identifying who's going to accept a loan, what types of customers we have, and so forth. And this can also help us in profiling by identifying the differences between the classes in the response variable that we're interested in. To help us understand better how this is done with discriminant analysis, we're going to look at our riding mowers data set, where again we're going to try and predict whether someone would purchase or not purchase a riding lawnmower based on the predictor variables of lot size and income. So if we look at the scatter plot of the data, and again this is a small data set, we see income on the x-axis, lot size on the y-axis, and then we have an indicator of who's an owner and who's not an owner. And the idea behind discriminant analysis is to draw a straight line that separates the data as much as possible. In other words, puts the owners into one group and the non-owners into another group. And so the line that we have here, you can see, does a pretty good job of that, except for these two owners are misclassified and these two non-owners would be misclassified. So we want to find a better line, if possible, that will do that. And just by eyeballing it, we can see that this line right here actually picks up this owner, and the error rate then would be smaller in that case. So that's the basic idea. It seems very simple, I know, and we'll talk more about the details, because we're not just going to be drawing lines. There's going to be distance functions that are used to measure where the center is for each of the groups, and then the distance between each of the points to the center. So let's look at another example. The loan acceptance data that we've looked at. We have an outcome, whether people are going to accept or not accept a loan. And the predictor variables we have are annual income and average monthly credit card spending, and there are several other variables, but we're just going to look at these two for now. And if we take a sample of the data, so we have only 200 customers, you can see that we have yeses and nos. Yeses are the circles, nos are the pluses. And the idea here is we want to find a line, again, that gives us the lowest error rate. So you could think of, well, let's just draw a line like that. Let's try like this. And this line is supposed to be straight, and I'm not doing a very good job of drawing a straight line. But if we drew that line, we would get all of the yeses classified correctly, but there's a bunch of nos that are not classified correctly. And so what we would need to do is go through and figure out what the error rate is for that line, and then maybe this line, and so forth, until we find the line that gives us the best separation between these two groups. Now, that's not easy to do. If you have 200 customers, what happens when you have all 5,000 customers? This is where we start to use our software and let the computer do the heavy lifting. So what are we going to do? What's the algorithm we're going to follow? This is going to be very similar to what we did with k-means. We're going to calculate a centroid for each of the categories, and each new record is going to be measured from the centroid and then classified according to the closest class, or the closest centroid. That's the main idea. How does this work in practice? Well, first of all, we have to define the centroid, and we're just going to use x bar, and this says of all of the observations we have in the first category, what's the average for the predictor variables. So this might very well be a vector, and one once we know what the centroid is, we can then say what distance are we going to use. The Euclidean distance is one that we've used with some of the other things we've done, k nearest neighbors, for example. And this is like Pythagoras' theorem for a right triangle. And if you have multiple dimensions, then you can see that formula. Although this should be a p, x sub p bar. This is useful, but has some drawbacks. There's sensitivity to variance and scale. So a better measure is the statistical distance, or the Mahalanobis distance. And the idea here is to basically form a z-score, a multivariate z-score. S is the covariance matrix, and so if you take x minus x bar, xi minus x bar, divided by the standard deviation sigma, and then square that whole thing. This is basically what we're doing when we calculate this statistical distance. However, we're doing it in multiple dimensions, in p dimensions. Once we have this distance, we then are going to estimate a discriminant function, and there are lots of different ways to do this. Jump is going to just say take the squared distance, and whichever one of those is smallest, that's going to give us our classification for a new output, or a new individual. So here you can see the squared distances for all of the data points for the non-owner and owner. So based on these distances, square distances, this one would be classified as a non-owner, misclassified as a non-owner, actually. We can also get the probability that goes along with this, and we'll look at that function in just a minute, but you can see the output in jump with the predicted class, and the ones with the stars are ones that are misclassified. And so you can see when we run this, we now only have 3 misclassified records instead of the 4 misclassified records that we saw when we first look at the data set. We can see what the discriminant functions look like. If we want to, and this is an output we'll see in jump, and we'll look at that in a different video. How do we calculate the probabilities that go along with these squared distances? Probability that an observation belongs to class K. So if we have m different classes, we can find the probability that each of the K, or each of the m classes are going to be predicted just by using this formula here. And then we would say the class with the highest probability is the one where membership is going to be assigned, and of course that's going to correspond to the one with the least distance. So what are the assumptions we have to make in order to do discriminant analysis? The first one is that we have what's called multivariate normality of the predictors. In other words, the x variables have a multivariate normal distribution, and discriminant analysis is most powerful when that's the case. However, even if we don't have multivariate normality, discriminant analysis is fairly robust as long as we have enough cases in the smallest class, and we'll say greater than 20. Other assumptions are that the correlation among the predictors are the same for the different classes, and there are procedures you can do to deal with that when that's not the case. But finally, if there are outliers, that can cause problems, and so you want to make sure to check for outliers before you do any of this sort of thing, and you can do that by the standard methods that we've looked at previously. How do we assess the performance? We're going to use confusion matrices and the misclassification or error rate. In this particular data set, we don't have a validation because the data set was too small. But same sort of thing that we did back in chapter 5. We're going to look for the lowest misclassification rates. We can improve on the discriminant analysis that we've described so far by incorporating prior probabilities. And this is done quite simply by adding a number to the squared distances for each of the classes when we're calculating the probability of belonging to a particular class. So for example, with the riding lawnmower data, we would say with equal prior probability we would have this formula to calculate the probability. But if we wanted to say a non-equal prior probability, say instead of 50% owners, 50% non-owners, we wanted to say 15% are owners, we would put that in here and in here, depending on which class we're talking about. So the calculation, if we're saying that there's 15% owners in the population and we want that reflected in the training data and the validation data, we would add 3.794 to the squared distance for the owner and 0.325 for the distance for non-owner. And when we plug those values into the different discriminant functions, we get different scores. The distance is now adjusted for owner and for non-owner, and we go with a non-owner classification for this record. What do we do if we have more than two classes? We use exactly the same procedure, and we come up with a probability for each record going to each of the classification categories, and whichever one has the highest value, highest probability, or the shortest distance is the one that we classify according to. So let's look at another example. Auto accidents. We've got the outcome. Max severity is either non-injury, non-fatal injury, or fatal injury, with predictors time of day, day of week, weather, type of road, surface, conditions, and so forth. Here's what the data looks like. We have all of our predictor variables, and then this is the output variable. This says airline, but it should say auto accident. So here's the result, and you can see that the actual outcomes are non-injury, non-injury, non-fatal, non-fatal, and so forth. And then we have predictions: no injury, no injury, fatal, so that's non-fatal. Here is misclassified as fatal. We have the probability of fatality is going to be 0.95. And we can see even more detail here when we look at the probabilities for each of the groups. These, of course, are again taken from the squared distances. So whichever one has the smallest squared distance, that's this one, that's going to be the one with the highest probability. And so you can get even more information there. To summarize, discriminant analysis is something that we are using to do classification with, and we're looking at the squared distance of a record from the average or the centroid for the category that we're trying to predict. We use that distance to come up with the probability, and depending on the metric that we use for the distance, we can take into account correlations, and there's a few assumptions that we have to make, like equal correlations within each of the classes, and we have to be sensitive to outliers. So we'll look at the data first. If there are outliers, figure out what to do with those. That's all I've got for this video. We'll see you in the next video when we look at some of the output from the textbook.